This conference will now be recorded.
Okay, Jawad's here, David's here. All right.
So, Bapi, where can I find this paper?
Here at the VLSI Test Symposium, I think I can give you a copy as well. I
Okay,
think
thanks.
so. I'll come to it. So I'm going to cover that in the opens. Anu, right?
Right,
Oh,
sorry. It takes a while to
no
mute and
worries.
unmute. Yeah.
David's okay. No worries, David. Take your time because we're going to cover the virtual summit. So the virtual summit is next week. So for those of registration is free, no charge. And you can find the ODSA sessions. So we've got a panel discussion. We've got Wei Feng from Alibaba, Rita's panel, a talk about the ODSA. This is mine, and then a whole bunch of lightning talks. Pretty good diverse collection. Bill, Manoj, Sham from Lattice, Sam, and Elko, and Manuel, and Jawad, and Vladimir from Ayer, and Brian Allison from IBM. So the way this is going to work is it's going to be played out in real time. And I think there's going to be an opportunity for, so Rita, to answer your question, at the time the session's live, you can sort of log in and be exposed to questions, any questions from the audience. And for that, Archana from OCP set up a whole bunch of training sessions last week, which I didn't attend either. But
yeah,
there's some material. And so we can look up the training, but the idea is that we log in and be online during our session, and you can sort of answer questions or participate.
Yeah,
but we need to get back to Archana need to respond to Archana by noon.
Yeah, I couldn't edit that spreadsheet. I tried to my iPad. That's the only thing I have access to.
Okay, so if you want me to, after this meeting, we can chat briefly, and I can update it on your behalf.
That's good.
Okay. Anybody else? If you can attend, I think it would be nice. If you're speaking and you have the.
I plan to attend. I just got back to Archana's May 6 email, and
okay.
So I need to do those homework that she told us to do. Yeah.
Yes, they've been under enormous strain getting this whole thing up and running. So, if you can make it, please respond by noon today.
Okay.
Any one of our speakers.
Yes. So I think I can send Archana an email, but also there is a place for me to put in as well. Yeah.
There is. Hang on. Give me 1 second if I stop sharing.
Go to I think go to shared, right?
Not shared here. It should be this sheet. Should be this sheet. So we should indicate our availability in this sheet. Rita, you want me to switch you to a yes in the sheet?
Oh, yeah, it's already yes here. I can see that.
You may want to also correct my name also.
Oh, yeah, that too, right? Oh, this I don't have, right? I can't. It's a protected cell. I'll try and correct.
No problem. I'm not going to most likely attend the whole thing. I have a conflict, but second half I'll attend. So.
Okay. Yeah. So the idea is maybe if you can reach out to our panelists and just tell them, hey, if you can be online, that'll be good.
Okay.
So Rita, would you reach out to Calvin Chung?
Good part?
Would you reach out to Kava and ask him whether
No,
he?
but
Yeah,
sure.
that would be great. Thank you.
I know a few people have conflicts at the same time, but we'll see. I think 1 or 2 people may be able to attend. That'd be great.
Does anybody else have any questions about the virtual summit? If you
Oh,
can make
yes.
it, please do. Yes, Bill.
She, in her email, she said, encourage all your colleagues to register. Is there any specific format, or do you think just send the OCP's materials to the colleagues?
Yes, or maybe we can. Do you want me to just take a screenshot of this and give it to you? This is our thing. If this is a session that you think your colleagues will like,
that would be great, because not only I want to say OCP, but what I want to say is that go to ODSA in OCP.
okay, I will send a screenshot.
Yeah.
Anybody, I'll send it with the minutes. At the end of I'll do the minutes immediately after the call.
Bapi, this is Elko. Otherwise, I can help go get it as well.
Okay, perfect. Thank you.
Hi, Bapi. And in your spreadsheet, I noticed there was a survey whether the speakers will be available for live Q&A.
Yes.
I will be available. I will be
You will be
dialing in.
available. Okay. All right. So
Thank
let's
you.
mark that. So there's some training material that all of us missed. Elko, who was just trying to show off, was apparently well behaved and attended the training sessions.
Yeah, I believe it is
I
recorded
tried.
as well.
I can't say I walked away a whole lot wiser, though. We'll see how it goes next week.
Thank you, Elko. You at least saved us on that. Saved us some blushes. Otherwise, nobody from this track would have attended. I think there were 3 people who attended. So I'm happy you did. Thank you. So there's some material. Manoj is essentially Q&A.
Yep.
Okay. Anybody else can make it? Is Sam online?
This is Manish. So what was this about, Manoj? Sorry, I just joined, Bapi.
Update you,
This is
Manish.
about
Often.
Okay. All right. So please. Okay, I've got 2 opens. I'll come back. All right. So we've got. If there's nothing, any last questions about the virtual summit? Okay, then David, your mic troubles all settled?
Yes.
Awesome.
I finally dialed in. I gave up on the computer.
Okay. So Jawad and David are have been doing a lot of work on power modeling and would like to share some of their work. Thank you so much for doing this. I'm going to make you, who do I make presenter first, Jawad or David?
So, Bapi, first I have few slides that would be followed up by David. So can you first please make me the presenter?
Yep. I'm going to make David a presenter as well so that you can, I don't know if one overrides it. Yeah, go ahead, please. Jawad, it's all yours.
Please let me know if you can see my screen.
Yes.
Okay. Well, thank you very much. So today we will report out a bit of update on chiplet power modeling work that we have been doing. So this work is primarily, the one that we show today is done by David Rajkov from Trace Systems. And in doing this work, we have a system.
Hey, Jawad?
Yes.
It looks like David is presenting a screen. So did you mean, were you going to present or was Jawad, excuse me, were you or David?
No, Jawad should present. I was playing with the controls trying to learn it and I screwed up. My apologies.
Oh, no worries. Then Jawad, you may need to share again.
Let's see.
Sorry, Jawad.
No worries. Let me know. Can you see my?
You're back.
Oh, okay. Yes. So in chiplet design exchange work stream, 5 of us have been working on this topic. This includes Jerry Frankel from SI2, Chris Ortiz from ANSYS, Faraz Shaukat from MACOM, and David Rajkov from Trace System has been doing quite a bit of this that he will present. So just to give you guys a little bit of background about chiplet design exchange, in this work stream, we are focused on a number of aspects of chiplet-based design. One of them that we will be talking a little bit about today is the power, thermal, and physical modeling data description of chiplets, and we are trying to come up with the mechanisms to do data representation such that it can the chiplet models can go from one kind of tool to the other type of tool, and you'll see a little bit of that today. Second thing is we have recently been working on POC package flow, and we'll present that at a later date. And we had previously worked on a chiplet catalog. If you look at our proof of concept work stream in ODSA, you probably are familiar with the pitchlet concept that we got, and we have a POC that we have demonstrated. So the idea about chiplet design exchange really is to enable the software development vehicle platform and then take it to a package and develop methodologies and develop mechanisms such that industry can benefit from this collaborative exercise. So in this particular aspect, what we did was that the work that we're going to show you is related to power modeling. And notice that package POC work is in flight. So what we did is ZGlue provided an example, which is a system built with chiplets. And it has it's a working system that includes a microcontroller and a number of sensors, temperature sensor, vibration, step counting, roll and pitch, and has some power management and other things. So it ended up being a pretty interesting use case that different companies contributed to. So at a very high level, the concept that we have is the following, and this is pretty much my last slide, and I'll hand it over to David from here. But let me just explain what is it that we are trying to achieve here in the power modeling. So our goal really is to come up with a power description format in a way such that the chiplet electronic data sheets can be written as opposed to the conventional PDFs, which every company has a different way of writing. So we want the chiplet marketplace to adopt some kind of a electronic data sheet format that is consumable by different EDAs, the EDA software. And that also results in creating a power description methodology when you just think about power, and that's what a little bit will show you. On this diagram on left-hand side, this is the OmniChip test case that David will show you. It has 7 chiplets, and for each chiplet, we kind of came up with its power description format that at this stage we haven't really described, but we will describe it in a white paper down the line. But essentially, it contains some metadata, then it contains some scenarios or mode of operation information that has electrical characteristic tables. It has some data about normalization of power, which is it specifies power at a certain point, but then you can normalize it to different voltages or PVT conditions. It also includes a little bit about the IO net listing. And then
quick question, if you don't mind.
Go ahead.
Anything about the workload?
That's right. We'll show you a little bit about the workload. So in this particular case, the workload is super simplistic. It's essentially a scenario. And actually, last meeting in CDX, we had some we had a presentation from MACOM where they described how they deal with this situation very early on. It's very interesting. We can probably talk about it a little bit more. But historically, we thought that we need super complicated workloads in the very beginning. But it turns out that a lot of the architects at a very early stage do simple things such that they make mock-ups or they do very simplistic Excel-based modeling. And down the line, when the design becomes more mature, at that stage, they move to more detailed power thermal modeling. So what we have been thinking that in chiplet design exchange, we want to make it easy for the early part of the design work by providing mechanisms such that power scenarios are more descriptive in nature. And David will show you how he took a couple of power scenarios in a very descriptive manner and did some very basic modeling with that. So as the design matures, you want to bring in something like UPM format, which is a lot more descriptive, and SI2 has done fascinating work on it. It is now an IEEE standard, where you can go all the way down to FSDB level detail power models and refine it. The only thing is that that happens as the design matures. So some of these tools that we are thinking about right now are really meant for the early stage of the design to help kickstart some of this effort. So that's the thinking behind it. So what you will see right now is Power Meter, which is a tool by Trace Systems. So David took all of this information from these chiplets and he created a model, and he will show you step by step how this whole thing was put together and what is our plan from there on. So this was, I believe, my last slide. Please attend our global summit. So I'm going to unshare and hand it over to David. David, it's all yours.
Thank you, Jawad. I just wanted to continue on what Jawad was saying about power. Let me know if my screen is not showing up. And one of the things, definitely the problem that is presented at CDX is what we want to do is model chiplet power and thermals. And we want to take existing tools and methodology and see how we can develop workflow that would allow us to estimate power and thermals. We took this specific work focuses on the power modeling aspect. How do we take PDF level data sheet? How do we convert it to readable format? And again, the intent is to have that in a actual tool readable file format that can be handed out between tools as necessary, and publish that to the industry for actual use. I have a few slides with lots of data, but overall, my slides would cover what the system looked like, what the initial system looked like, how we model that, cover a few aspects of the power modeling details, and what a system power model needs to actually be able to do, and what it actually does. It actually meets those goals, and how we define the scenarios and show off some results as well. The flow, looking at the flow, the way we started it, we have chiplet power data. In this case, it came to us as a PDF file format, what you would typically get right now. We can, if somebody has UPMs, we can take that and use that as well for power definition. I want to acknowledge actually two groups, CDX and specifically the group for seeding the effort with reference design data, and definitely want to acknowledge SI2 for the awesome work that was done on the power modeling side in defining the IEEE 2460 standard. I think that's an awesome step forward in power modeling, and it's actually great. I'm very excited about the whole power modeling aspect anyway. So looking at the flow, so the data came to us in that format, and what we wanted to do is perform power analysis by using some defined use cases we wanted to be able to model the whole system and definitely show how that information can be used to perform power analysis. And the expected output in this case would be twofold. One is UPM to hand off to other power analysis tools, and data to be handed off for thermal analysis, some detailed data that I think is necessary to do proper thermal analysis as well. The system itself, it's tiny, but it's already complex. It's a 7-chip system. It's a very good vehicle to show us how we can we model all different aspects of how it works, what power is, how things are connected together. As I stated at the beginning, power was a data sheet. The question is, okay, can we convert that data into a tool readable format and let the tool handle it? Can the tool handle it? How do we do that? Can the tool understand it? What does the system model looks like? Can we define a system model? And for scenario definition, we chose 2 scenarios that show the mechanics of how the scenario definition works and how power analysis works. And then the output of the power analysis is twofold. One is power, average power, maximum current as well, obviously, if that comes out of that. And the other aspect is actually total energy consumed. In this specific case, it was interesting to see this small chip, if it's used in a consumer device, how long the battery would last.
How about, maybe quick question, how about for output? Is temperature an output also?
We did not perform thermal analysis yet, but temperature can be output, obviously, with the physical data and what power data producing temperature is also a possibility. That's the next step of the flow that we want to get to.
Okay. I think, yeah, especially, for power densities and like compute chiplets and stuff is going to be very critical to get that kind of
absolutely. I absolutely share your thoughts on that, and definitely we want to get to thermals as well. But see, here's the thing: to get to thermals, we have to be able to get good power data. That includes early on be able to model different use cases. What does the interaction between various blocks looks like, right? Try to model that and get power data that way, and also see on die whether we can model different blocks with their own power so that we can see die level hotspots. All right, and for that we need good models and good tools to be able to handle all of that. And then this is what I'm trying to focus on. Next step would definitely be to get to thermal simulation.
Okay.
In terms of modeling this. In terms of modeling the system, it's twofold. One is we wanted to model the physical aspect of the system, and on the left side, showing the actual physical hierarchy. The package substrate is shown as a PCB in this case. It's modeled as a board. Yes.
Sorry. In the previous slide, in 5, what is the nature of power data in a data sheet? What kind of information do you typically get?
So it varies a lot. I have some examples down the slides. Overall, power data is in 3 formats: tables, equations, and waveforms, and they depend on external parameters. In some cases, data can be specified as actual graphs. In the PDF data sheet, but that can be translated into a table as well. I have example of that as well.
Thank you.
Yep,
for the system model, do you assume these are connected via interposer, or what kind of connections between the chiplets?
Yeah, in this case, the physical connection is assumed to be like a board. And I think it's a package substrate. It's actually LGA package with the chips on top.
Okay, thanks.
But yeah, since we haven't gotten to thermals yet, we haven't spent a lot of time on trying to perfect the physical modeling of the system yet. And on the right side here is shown the supply connectivity at the 2 levels, showing how it comes from the board and from the LGA to the chiplet packages and into the chiplet dies. We wanted to model that. I wanted to show that specifically because there's usually a difference between what package pins, die level pins, and I wanted to show that it is possible to actually model the actual physical connections, right? In case there are systems that would vary how packages connect things inside, we can handle that as well.
Is this, by the way, dynamic power, or does it comprehend things like leakage?
So the data sheet, when they specify, they don't necessarily break it out. Specifically for the microcontroller piece, power is specified as one total power number, but it's also voltage and temperature dependent. I think it was temperature. I'm sure it's voltage dependent. I need to double check if it was temperature dependent as well. So in which
By
case,
the way, I think it'd be good if you show an example of the data sheet. Like what kind of information?
I have a couple of examples down the slides as well.
Oh, very good. Thank
you. Yeah. Overall, as I mentioned, power model, a system level power model needs to fit it needs to meet several goals. One is it needs to be compatible with existing flows and data. And specifically in this case, 2416 is fully compatible with Liberty data. So that allows flow compatibility that we are not going to break any flows if we use this data, and we can move from Liberty into 2416 very, in a very clean way because it supports all the data. Additionally, 2416 actually enhances quite a bit the modeling of gate level data. That's die level component data. It enhances with power contributors and energy contributors, which allow for additional power estimation capabilities to be built on top. Expanding it to the system level, we need to be able to model states of the IPs. And IP, I'm using the term very loosely. IP could mean a simple IP level block, could mean a full die. It could mean multiple dies as well. Actually, right? It needs to be able to expand to that level, and it needs to, as I mentioned, in data sheets typically we have three ways to represent the data: equations, tables, and waveforms. And there's a reason for that. In many cases, the data in datasheet actually comes from silicon measurement, and in that case, it would be actual measured data. It looks like graphs. It looks like tables. In some cases, it could be combination of the two, showing it as a waveform that when it's on, it's this much power. When it's off, it's this much power, and then the time it's off, it's you calculate it that way. I have an example of that. So it needs to be fairly flexible in how it handles the power data. And one thing that 2416 does awesome is basically link the system level model, how you define the use cases and parameters to the lower level gate level power data. So it's actually to build a two-level representation that does quite a bit of accurate power estimation. And diving into examples, there's a lot of questions. I'm actually happy about that, about how data is represented. In this case, I'm showing the data sheet for the TI's battery charger. It's a small piece of IP, but it's kind of typical of the data that is being presented to users. As you can see on the right side, on the top is what TI has produced as current consumption. X-axis is the battery voltage that comes in, and on the y-axis is the current drawn. And there are multiple graphs actually to show what how current would actually change with temperature. So we took that into a two-index table. One index is the voltage, one index is temperature. We put in the values from the graph. And those are equations which are, since we produce the final output is expected to be power, we convert those values into into milliwatts, where BAT is actually the name of the battery supply. So we get an equation that gives us power. In this case, it matches it converts the current into milliwatts. So with this, this kind of demonstrates how we can handle how it is possible for a tool to actually handle table power data. typically what you get from measurements if from chiplet suppliers. Next example is, I think it's very cool, is the waveform. That's the waveform for the temp sensor. It shows power consumption during sensing operation. And it also, the thing is that this waveform depends on how often the temperature sensing is being done. In this case, the time between two sense operations is controlled by external parameter. The net result of that, the way we modeled it into the tool, was to create a waveform that was parameter dependent, where both the time and the power would be actually equations. This allows us, when a user comes in and specifies what the parameter value would be, in this case, it's the time between sensing operations, we can translate that into we can dynamically translate that into a waveform and compute power based off of that. Okay, moving on to the actually the biggest piece of power consumer on this system is the microcontroller unit. That unit is actually a system of its own. It has more than 20 sub blocks. It has integrated power converter. It has LDO, and DC to DC converter. And just for the we can model the whole thing, but in order to stay sane and for brevity to show what the results will look like, we focused on two pieces of the system. That's the CPU and the radio. The thing is, these two pieces represent typical system where you would have a computing unit and you would have IO unit, and the computing unit would do its thing, and then the IO would transfer data back and forth. And there is always the trade-off between, do I compute locally or do I send it off? Do I send off that data to the outside world? And the cost of both cases is power. And the question is, can we model the difference in the different use cases and see what the power consumption is and make the necessary trade-off how we want the whole system to operate. In this case, again, as I mentioned, we modeled this microcontroller unit as a system of its own with two pieces. One is the CPU subsystem. CPU subsystem is actually ARM core. It has very simple parameters which are typical for CPU units. It specifies whether the CPU operates off of the cache or not, what the frequency of operation is, and what kind of memory it's using to actually store its data. And the power for that actually comes as conditional equation. It's frequency and voltage dependent, obviously, but also it depends on whether it's using the internal, which of the internal power supply is using in what setting, and also whether it's running off of the cache or not. So this demonstrates how an equation can be used to actually build a how to translate the data sheet into equation and use it to compute power based out of that. Overall setup for the microcontroller unit then takes these the parameters for the CPU and takes also the parameters for the radio IP, how it operates, what TX mode, whether it's on off, or at what speeds it actually operates, and actually what power levels. And it builds a new model that depends on 8 different parameters, and those parameters get passed down to the hierarchies to estimate power. And here's how this model, the small model, looks like when we want to model it over time and in a use case. In this case, what we wanted to model is one use case where the system would wake up, it would compute something, then it would send it off to outside world, it would receive some data back, and then it would compute something more, but for that it actually would run at high frequency, and then it will doze off, and actually it would doze off here, and then the voltages will slowly drop. So this would be a good example of a system that's DVFS. It wakes up, does some work, transmit and get data back, and goes back to sleep. You can see the power profile out of that, how it varies over time. We can definitely get what the currents were, and we can see what the energy consumption was, and with that we can estimate, hey, you know what, this is what my battery life is going to look like. We can see the difference between RX power and TX power, and see how much each one is costing us. Are we sending too much data? The thing is, in this particular case, what Jawad pointed out, that because of all the overhead and the payload size, it actually costs us about the same amount of power to send 1 bit or to send 10 bits. So we want to be cognizant about how much data we actually want to send. And this is definitely something that can be modeled in a system level model like that, and see, are we sending enough data? Are we sending too much data, too little, small chunks, too often, and so on. So this is a scenario that can be played out and compared. Now, going back into the full system that we want to model, that's the 7-chiplet subsystem, the OmniChip. There were 2 use cases that we settled down on. One is industrial case, which is very, very simple. It has an industrial case where it's measuring, it's used as a temp sensor. In this case, only the temp sensor and the microcontroller unit would be operating. And we wanted to model how the temp sensor is measuring temperature all the time. The microcontroller unit would wake up once every second to do local processing and gather data, things like that for a little bit of time. And then every minute it would wake up and send all that data, all that processed data to the through Bluetooth somewhere to the outside world, and then receive some data back and go back to sleep. Shown off here is the microcontroller unit, how it wakes up every second for a little bit of time to do processing. Radio is off most of the time, and only here towards the end it wakes up and does transmit and receive after that, and everything goes back to sleep at the beginning and moves back. Temp sensor is on all the time. It's doing continuous operation at 4 samples per second. And actually, it's 4 samples per second, I think. And it's transmitting, it's translating, it's talking to the microcontroller at 10 kilohertz on the serial bus. This was a simple case. Looking at the power, as expected, we see the little peaks here when the CPU would wake up and do a little bit of local processing. That's the little power. And then at the end is where the big power consumer is, the way things wake up at maximum speed and data is sent and received. Case number 2 was a little bit more complicated. It's a consumer case, and in this case, we wanted to model a watch kind of a product. Pretty much all chiplets are on during this operation. Accelerometer is typically running at a low power mode and just sensing what is happening, how it's moving. Every second, it wakes up and does precision measurement. It switches to precision mode. You can see this, the low power mode drops every second and the precision mode goes up to 100%. This the intent here to show off between a handoff between different modes of operation and different states for the given chiplet. Microcontroller does similar operation like before. It would wake up every second, do a little bit of local processing. But then in the end, actually, since it has accumulated a lot of data during this time, it would transmit for about 90% of a second. For 0.8 seconds, it would transmit and then receive for 0.2 seconds some data back from to a phone or to external device, and it's going to do some local processing. This piece is on all the time. Temp sensor is again being a consumer device. It's all on all the time. But in this case, it samples at 0.25 samples per second. That's 1 sample every 4 seconds. It samples what the temperature is, and it's running at very low 1 kilohertz serial bus to transfer all the data. The intent here is, okay, you know what, we want to get the lowest power as possible, so things have been turned down as far as possible, and things will wake up only when necessary and transfer it only at the very end when necessary. So this is one case where we're trying to do trade-offs between, hey, you know what, we want to save as much power as possible. What does that look like? Similar report out. Again, we see the little peaks, a little bit of the power all the time, and also see a little bit of, and we see the same power towards the end. It's because, again, power in this case is dominated by the CPU running and by all the I/O operation that's happening. That is what dominates power in this case. Now, we mentioned the thermals and temperatures, and I wanted to share a piece, a result from a different project that we have been working on. This is an example of an SoC, and luckily, this is what we get. We got two cases here, where in one case we run at higher power, but overall power density, maximum power density is lower. While in this case, we do run at a lower overall power. However, the maximum power density is much higher. It's almost double what it was, and it's these two CPU cores here. So now, the question, okay, so which case would have worse hotspot temperature would actually depend a lot on what the external system looks like. It's not one-way answer for this. It's not obvious what the answer is. And for this, it's reasons like this why we need to go and do thermal analysis. Again, usually thermals will be driven by the power density, but also by overall power. So when we have cases like this where power goes one way and then the power density goes the other way, it's very hard without actual thermal simulation to find out, to guess what the outcome would be. Actually, I wanted to pause for a moment and ask if there are any questions. I kind of plowed through these slides. I hope if you have any questions, feel free to reach out after that, after the meeting. That's fine too. I will be more than happy to answer. And in summary, we were able to do a detailed power analysis for a 7-chiplet system, showing off different use cases, how they operate, showing different styles of how data is represented. Most importantly, we have a tool that can handle all of that to produce power. It can handle the scenarios, complex scenarios. We can handle the between chiplet states. We can model things over time, power, current, energy. We can model maximum current, current delta, power beta, and so on. And out of this, we can generate detailed power information that can be fed into thermal analysis. Definitely what we learned out of this is that 2416 style of modeling of power is definitely one way to go about this. And we would like to go about that, to go that way and use 2416 as a basis for handing off power data for chiplets in a full readable format. That's very important to have a full readable format to be able to perform all the various simulations for power and thermals. We expect to publish white papers with the results, how we went about the flow, how we model things. And most importantly, we plan to continue the collaboration both within CDX and within SIQ CPM. Our next steps are fairly clear: get thermals done and see what the results are out of that, and definitely publish how this representation of this data would actually look like in an actual 2416 file format. And that was my last slide. Thank you very much for the time. Yes.
Yeah, good talk. One question. So for what's the outcome? So you would the system make some kind of suggestion for the better power interference, like when you do when you place the part chiplet move along, for example, maybe one on left, the other on the right, and then you move along, that will improve the power integrity. So what's the result of the of the output? How do you show the output?
So the focus in this work was to model power in different use cases. Basically, being able to come in and specify this is the workload I have, and this is the power I have in these in these representations. I won't say funny; they're not funny. They're actually very serious representations. Tell me what my power is, and tell me what my power is for each of the chiplets over time. Now, with that, I can definitely the next one possible next step is to go and say, okay, what is worst case for this whole system? What is the worst case in terms of power consumption, and also in terms of thermals, right? Analysis can be performed at different points in time, and we can monitor how things change over time, right? If you come in later on at the later date and say, hey, you know what, my power actually changed from 10 to 20, what happens to my system? We can perform the analysis automatically. Now, as far as suggesting what a possible solution for this would look like, at this stage, the expectation is that the user would be able to play a little bit with the configuration. And actually, we can explore, obviously, right, with this kind of modeling, we can explore different physical options and see which one is better, which one is worse.
Mm-hmm. And another like a critical item for the power integrity is the number of the capacitors and the type of capacitor, and also of the combination of different kind of capacitance of the capacitors. Right. So the system will also simulate this kind of, for example, maybe I put like how many?
Yeah. So this time the focus here is solely on current consumption, on average power over time. Definitely, we are not looking at the cycle per cycle performance of the system.
Okay, thank you.
Right. For decap capacitors, you would need cycle by cycle accuracy.
Mm-hmm. Thank you.
Yeah, you're welcome.
So for the use cases, you're depending on the experience of the user to model the use case of interest, right? In this case, like Jawad gave you, okay.
Correct. In this case, the use case definition came from Jawad. But definitely there's an option here where we can, if there's a simulation at the die level, we can go in and say, okay, this is how the system operates, this is what's coming off, this is what's coming on, and we can model that. But then again, so here's the thing. The focus here is on the architecture side, right? How do I architect this whole thing to work? And when I come in and architect this, I know what components I have, I know what their consumption is, and I kind of have a guess of how the system wants to operate. Definitely, as things progress with the flow, I understand that things change, but we already have that scenario defined in place, and it's very easy to come back in and say, you know what, I want to expand this time a little bit and see what happens, right? They say, for this case, for temp sensor, say what we can easily model what will happen if I sample more often, versus less often. I can come in. And the other thing to remember is this: being able to specify architecture in a system like this makes it very nicely to hand off to the next level in the design flow, right? Engineers would understand when the system was designed, what thinking was in mind, right? They won't go off and change the temperature sensor to be reading it, more often because it's cool, right? They would understand that, hey, it was defined to be at this frequency, and because power costs this much, right? And if we need to make a change to how the system operates, we can come back and change that and see what the impact, what the cost is. In this case, cost is power.
Okay. Thank you. Any other questions for David or Jawad?
This is Marshall Goldberg from Lattice.
Hi, Marshall.
Hello. David, I don't know if this is a question specifically for you, but I'd like to understand what is the business model for using your services in this project. I mean, I would certainly understand if we were making our own semiconductor, but if this is a type of open source MCM, who do we propose will pay for this work?
Okay. Can I get back to you with the answer to that?
Oh, yes, of course. Of course. Thank you.
Yeah, I need to think for a moment about this and discuss with Jawad and Paulie and Bapi how this works. Can you shoot me off email to david@tracesystems.com, and we can continue with the discussion. Thank you for the question, though.
It's my pleasure. Thank you for the presentation. It's very interesting.
This is Jerry Frankel from SI2. I'd like to make just a couple of quick comments. First of all, David, great presentation, very interesting, great work.
Yes, thank you very much, Jerry. And it builds on a lot on the work that you guys have done at SI2 and defining the 2416.
Right. What I wanted to mention to the group is that SI2 has organized a tutorial for DAC that focuses on using 2416 for power modeling and system level analysis. So if you'd like to learn more and go into more detail about how these models are built, how these models can be used, what sort of information can you get out of them, that sort of thing. We've got a 90-minute tutorial scheduled for Monday at DAC. Thrace Systems is involved with that and will be presenting. And there's also additional work being done by IBM, North Carolina State University, and ANSYS. So for more information, you can certainly contact David. You can contact me. But if you'd like to go into depth on this, there's a great opportunity at DAC. So I just wanted to make people aware of that.
Okay. Any other questions?
So I'd just like to make one final remark here that we in CDX group are open to participation. So folks here who have interest in defining and understanding power scenarios, vectors, and seeing how we can do pairwise optimizations once we have this basic methodology and framework in place and extend this work in the direction of power integrity, please come over and join us in CDX.
All right.
All right. Thank you all for listening to me. Thank you for the questions. Appreciate it.
Thanks, David. So we've got a few minutes. Let me do a quick round. If anybody have any opens? Let me, Ali, Anu.
I'm good, thanks.
No, thanks. I'm good.
All right. Chris, Chang.
I'm good.
Okay. Dan or David Allen?
No, Bapi.
Elko Faraz?
No, nothing here.
No.
JP?
I'm good, Bapi. Thank you.
Jinshri or Manish?
No, good. Thanks, Bapi.
Oh,
Manoj, Marshall, Paul? Nobody with any opens? Okay.
No, thanks.
Okay. Reza, Rita?
No, thank you.
Scott, Sean?
I'm good. Thanks.
All right,
course.
Tawfiq, you got to deliver something. Bill, Tawfiq or Bill? Nothing?
No open, thanks.
Okay. All right. So then, two quick things. One is, we, as we said at the beginning, there's a paper on test that a group of us put together. It's available online at the VLSI Test Symposium. I think you have to register for it as a session. It's a recorded session and a paper. So it's got people from Advantas, Teradyne, Facebook, NVIDIA, and we go into basically the test challenges for chiplets in a marketplace. Please take a look. Outside of that, please attend the summit next week and have a good weekend and everything. Thank you.
Thank you.
Thank you. Thank you.
Thank you, Bucky.
Bye.
Thank you.